Chemical reactions. Excuse me. We're going to look at different types of chemical reactions, classify them into groups, and then look at the theory behind the chemical reactions, and then look at equilibrium a little bit. We won't go into as much depth as I do with my general chemistry class, just enough to get our feet wet. And then we'll look at Le Chatelier's principle at the end. Let's see. Did I put that one? There's a Le Chatelier's lab. Yes. We'll have that one before Thanksgiving break. That's good. All right. Types of chemical reactions. All right, we've already been introduced to some of these ideas already, but they bear repeating. A chemical reaction is, by definition, any process that causes a chemical change. In other words, the products of the chemical reaction have different identities, chemical identities, than the reactants. And there are major types of chemical reactions, and you can classify a chemical reaction as more than one type. So these are functionally defined. And these are just a few. There are separate slides for each one, so I'm not gonna belabor these. Combination, decomposition, single replacement, double replacement, oxidation reduction, and so forth. Okay, a combination reaction is, by definition, any reaction that takes simple and makes complex. And the simplest type is to have some type of elements on the reactant side. And let's see, we've balanced equations, haven't we? Yeah, okay. So I don't have to explain that. Our example there is, say, calcium plus sulfur yields calcium sulfide. We have two elements, makes a compound. That is the simplest form of combination reactions. Sometimes you'll see, it's also called a synthesis. Either one is a proper name. This is usually what we mean with a synthesis reaction, but you can have simple compounds making a more complex compound. That's also permissible. And by the way, this is not just a synthesis. This is an oxidation reduction. And I'll have to define that for you in a few minutes. Decomposition is just the reverse. If we take this arrow and switch the directions, that would be decomposition. A displacement reaction is one in which you have an element reacting with a compound. And the example there is iron with copper sulfate. I think we did this one in class, where we had, let's see, what was the name of that lab? Signs of chemical change. Yeah, I think we did this one in that lab, where this metal replaces that metal. So we end up with, let's see, yeah, that's right. And plus the free copper. All they did was swap places. This is also an oxidation reduction. It's a single replacement or a displacement reaction. And it's also an oxidation reduction reaction. So both types are valid for that one. A double replacement usually occurs between two different soluble salts. Silver nitrate in solution plus, let's see, what we use sodium chloride. Okay. Sodium chloride in solution. And the easiest way to think of this one is just take the cations or the metals and swap places. So sodium and nitrate go together. And then you look that up in your solubility chart. We talked about that before, didn't we? Solubility chart with the grayed out. Maybe we didn't. Let me see. If I have a slide on it in here, that means that's new information. I don't see it though. We must have talked about it before. Yeah. So this compound is soluble, and then the silver and the chloride combine to make a solid, a precipitate. That's a double replacement reaction. And many of the double replacements have a precipitated compound as a product. And this, in effect, is what drives the reaction. Because this being a solid is removed from the reaction environment. It's no longer in solution. So when you move that one, it drives the reaction over there to replace it as it disappears. And we'll talk about that a little more when we get to Le Chatelier. Okay, combustion. This was a double replacement. Let's see, this one might work better. A double replace. That was a double replacement. Now we've got a combustion reaction. A combustion reaction always has one of the reactants as oxygen gas. That's a combustion reaction. In this case, our example is propane. So that's a gas plus oxygen gas yields, and complete combustion yields carbon dioxide and water for hydrocarbons. Now you can have a combustion reaction with something else like ammonia with nitrogen in it, and that would give you different products, of course. Let's see, it's 5 and 3 and 4. So this is a combustion reaction. It's also an oxidation reaction. So we're seeing some crossovers there, especially with the oxidation reduction. Okay, this reaction, just to test your knowledge, we take a complex and make simpler. That's a decomposition reaction. Okay. We made some element, oxygen, but we didn't always make elements. We didn't make elements as a product for everything. Okay, let's see if we can classify. Our choices are combination, decomposition, displacement, exchange, or combustion. All right, so the first one, we've got an element and a compound, and on the other side, we have a compound with that element in it, and then part of the compound is an element. So that's single replacement, right? Or a displacement. Same thing. Now you may be wondering, why do I have to bother learning all these names for reactions? Right? I already know how to balance equations. If we can categorize equations, reactions into certain categories, they have similarities in the way they behave. So it's helpful to look at them in terms of what family they belong to. How about hydrochloric acid or hydrogen chloride? This is a gas. Hydrogen chloride and ammonia produces ammonium chloride. That's a combination reaction. Also, you got a couple of reactants makes only one product, or a synthesis reaction. And this one has ammonia and oxygen. That's a combustion reaction. Now, we weren't given oxidation reduction as a possibility, but the first one is an oxidation reduction, and the second one's not. The third one is also an oxidation reduction. Now we define what I'm talking about. An oxidation reduction reaction is any reaction in which electrons are transferred from one reactant to another, or one element in a reactant to another element in another reactant. You have to have electron transfers in order to have oxidation reduction. If there are no electron transfers, then that's not a redox. Now, one of the simplest ways, if it's available, to determine oxidation reduction is if you start off with an element, like we did with this one, magnesium metal plus, was it copper sulfate, wasn't it? Aqueous. Now, that metal is in the compound, and the copper comes out as an element. If you have an element on one side and it ends up in a compound on the other side, that's always oxidation reduction. Or if it's in a compound on one side and it ends up as an element on the other side, that's another definite clue to an oxidation reduction. Okay, so if we don't have that available to us, combustion reactions are like that, right? Oxygen is an element here, and it's in a compound on the other side, okay? But if we don't have that available to us, then we need a way of bookkeeping electrons in each of the elements that are in the reactants and products. If we can track the number, the movement of electrons, then we can decide whether it's an oxidation reduction. Because you may have a complex reaction without elements, free elements on either side, and it's still an oxidation reduction reaction. But the only way we can tell that is to track the movement of electrons, and that's where oxidation states come in, or oxidation numbers. I'm going to show you how to do that in just a second. There are some rules, of course. Rule number one, the oxidation number of an element in its most stable state at room temperature and 1 atmosphere pressure is 0. So if you have an element written like, I don't know, like this, that's always oxidation state 0. Okay. It's not the same as a charge. It could be related to a charge, but it doesn't have to be, right? This is still a bookkeeping scheme. It doesn't say that we have to have a charge. In this case, we don't have a charge, and our oxidation number is 0. If there is a charge on a monatomic ion, say we had silver nitrate in solution, we know that it's going to be like this. That's actually what it is in solution. Okay? That silver has an oxidation number of +1. Okay? Now, we'll have to calculate these, and we need some more rules. The oxidation number of alkali metals in a compound that's always +1. Alkaline earths, always +2. So lithium, sodium, potassium, rubidium, if they're in compounds, they will always be oxidation number +1. Beryllium, magnesium, calcium, strontium, barium, they're always +2 in compounds. That's the way we count them. We have to have these rules because some of the elements that are in compounds have so many possibilities that they have to be calculated on the spot. So we nail these down for the purposes of the ability to calculate the rest of them. Hydrogen. If hydrogen is the first element in a compound, it's always +1, like this one. Hydrogen chloride gas, that's a +1. Which means, what does chlorine have to be? Has to be a -1, right? Because that compound is neutral. So we have to balance oxidation numbers the same way we would charges. Okay. Now, if hydrogen is in a compound with a metal first, like aluminum hydride, the aluminum is the positive charge. And hydrogen now is a -1. So that means aluminum has to be a +3. Okay. Oxidation number for oxygen in any compound is a -2, except for peroxides. So if we say water, that's a -2, right? And we've already got a rule for hydrogen. It's +1, and that's 2 pluses and a -2, it balances. But if we got a peroxide, like you have hydrogen peroxide in your medicine cabinet, right? Each one of those oxygens is a -1. And if we drew the structure out like this, that group would be a -2. So each oxygen is a -1. That's characteristic of peroxides. For neutral compounds, I've already mentioned this one. For neutral compounds, the sum of all the oxidation numbers for all the elements in the compound must add up to 0. If you have a polyatomic ion, then they must add up to the charge on the polyatomic. For instance, if we have nitrate with a -1 charge, we have to add all these up to be a -1. We know that oxygen's a -2, right? So it contributes how many to that compound? 2 times 3 is a -6, right? So if we got to keep one of these negatives out to be sure that it has a negative charge, that means we only need to neutralize 5 of those negatives, right? So that means nitrogen would be a +5 because there's only one of them. So we check ourselves. If this oxygens contribute that, and that nitrogen contributes that, add them together, you get a -1. All right. So let's see if we learned anything. We can apply the rules and calculate the oxidation numbers for those that have variable possibilities. Potassium dichromate. Now we know from when we did nomenclature, we had that chart of polyatomic ions. We know that this dichromate has a -2 charge. We can do it that way. We can just separate that out and say -2. And we know this one is an alkali metal, it's a +1. So we can do the rest of them like that, or we can do the whole thing all together. We'll do it that way first. So this one has to be +1 by our rules. And oxygen has to be a -2 by our rules. But we don't know what chromium is. There's no rule for chromium. So 2 times +1 is +2. That's what potassium contributes. Oxygen is 7 times -2 is a -14, what it contributes. Now let's put these together. -12, right? So that means those two chromiums have to be +12 together, right? +12, that means each one has to be a +6. Okay? And if you did the dichromate ion separately, you should end up with that same value. Oh, this is probably animated. Yeah, there it is. So we got a carbonate polyatomic ion. Right? So we got a -2 for each one of these. It's a -6 total. But we still need to have 2 of those minuses unneutralized to keep that charge. That means we only have to neutralize -4 with that one carbon. That means that one carbon is a +4. And that's what it should show us. There we go. Okay. I'll just leave that up there. Manganese oxide. Okay. I think we've done some of this before, right? In nomenclature. Because in order to name this as a type 2 compound, we have to know what the charge is on that manganese, right? So if this is a -2, then a -4 total, that's a +4. So if we were to name it, it would be manganese 4 oxide. And there's our confirmation. Now, how about this one? PCl5. We don't have a rule for chloride. We should have had a rule. Hold on. No, it's not there. Fluoride. When fluorine is in a compound, it's always -1. Always. When the other halogens are in compounds, they can vary. That's why if you look at the box up there, you see a list of, looks like charges in the upper right-hand corner for each one. Fluorine only has one. Chlorine has several, bromine, iodine, astatine, they all have several. Those are oxidation states. Those are not charges necessarily. But if we don't make a choice, then we can't determine either one. Okay. So what you do is, if you're faced with a problem like this, where you have 2 nonmetals, this would be a covalent compound, brain farts. You choose the more electronegative, you settle on what it is. And since chlorine's a halogen, in this case, we're going to give chlorine a -1, just like fluorine. That means -5, and phosphorus would have to be a +5. If we don't do that, then we're stuck. We can't move. And if we say that phosphorus is a -3, we can't say that, because we can only say phosphorus is a -3 if it's combined with a metal. Then it's an ionic compound and it has to assume a charge. But in these covalent compounds, when you have 2 nonmetals, you have to pick. I think that's why we put that one in there. There we go. Now, sulfur tetrafluoride, that's not a problem, because fluorine is always -1. I need to change that slide, don't I? Add fluorine in there. that means with a -4 total, that sulfur is a +4. All right. Well, that also drives home the point. When you've got two nonmetals, it's a covalent compound, there can be no charges. So in that, with that being said, these have to be bookkeeping numbers. That's it. We're not saying they're charges because they're sharing electrons. All right. So now that we can determine what the oxidation number is for each one, we can do that for reactants and products for each of the elements. And if an element is a different oxidation number on one side than the other, then we know electrons have moved. Now, this is an easy one because this is a synthesis reaction, and we've got two elements on the left-hand side and compound on the right. We know it's oxidation reduction. But in order to know how many electrons have actually moved, we have to assign oxidation numbers to them. All right. So let me clear the board. We'll use this very simple reaction to show the bookkeeping scheme extended to reactions. So calcium plus chlorine, and we're leaving the phases out for now. Like that. Okay. So these are 0, 0. This is a +2, and this is a -1. Okay. Now, what I like to do is draw tie lines to show which ones moved where. So in this case, if we go from this 0 to that +2, how did it get to +2? It had to lose 2 electrons for each calcium, right? If it loses 2 electrons, that's 2 negatives are gone, but the positives stay behind. So that means 2 positives are the imbalance, we would say. So we had a loss of 2 electrons for each calcium. Okay. For chlorine, we went from a 0 to a -1. That means we had to gain 1 electron per chlorine. But how many chlorines are there? 2. So times 2 equals 2 electrons total times 1 equals 2 electrons total. That's always the case. When the loss is a certain number of electrons, the gain has to be exactly the same number. And let's see. I want to steal my own thunder. Let me check the graph. Yeah, okay. I got a slide coming up. So I don't need to do that right now. How about assign an oxidation number for sulfur in sulfuric acid, H2SO4? Well, we know hydrogen's first, so it has to be a +1. Oxygen's a -2. And the whole thing is neutral. So we have -8 contributed by the oxygens, a +2 contributed by the hydrogens. So that's a -6 that has to be balanced by that 1 sulfur. +6 for that sulfur. Okay. Okay. So I'm going to leave this one up here so that I can talk about what happened. When there is a loss of electrons, we call that oxidation. When there's a gain of electrons, we call that reduction. Okay. Now, they always occur together. If you've got an oxidation, you have to have a reduction. They cannot occur separate from one another. And it's actually logical. If you had one without the other one, you build up a static charge. Right? And in chemical reactions, we don't get static charges. That's physics. They do, Van de Graaff generators and rubbing, was it silk on a glass rod and rabbit fur on a, or is it rabbit fur on a glass rod? Which one? It's silk on one and rabbit fur on the other. Glass rod versus a rubber rod. But you build up a static charge. In chemistry, we don't do that. We don't have static charges. So when you do one, you have to do the other. And if this is oxidized, then it becomes the agent by which reduction is accomplished. So this is the reducing agent, which just means that it caused the reduction, and vice versa. This one then would be the cause of the oxidation, the oxidizing agent. Okay. Now, if you're trying to remember which one's oxidation and which one's reduction, there's a neat little mnemonic device, oil rig, right? Okay. Oxidation is loss. Reduction is gain. Okay. This just puts everything together in one place. Now, I'm not partial to using this, but since your book talks about it, I kept the slide in here. When oxidation occurs, the oxidation number increases. In other words, it gets more positive. So that could be a change in negative numbers, right? We could start out at -7 and end up at -4. We've increased, we've gone toward the positive with that, which means that we've lost electrons. And then reduction is a decrease in the oxidation number. We could start at +7 and end up at 1. +1, you're still positive, but you move toward the negative end, and that's reduction. Moving toward the negative means you're adding electron. You're adding, think of it that way. You're adding electrons. All right. So let's see. Let's clear the board. In the reaction listed below, we have copper and silver nitrate reacting with one another to give silver metal and copper nitrate. What is oxidized and what acts as the reducing agent? Well, whatever is oxidized acts as the reducing agent. The oxidized species causes reduction. That makes it the reducing agent. So all we have to do is find the one that's oxidized. So we have copper and silver nitrate, and we end up with silver and let's see, there are 2 of them. That's what I thought. So that means we need 2 here and 2 here, right? Yep. Okay. So elements are always 0. So look at this one. This is a polyatomic ion with a -1 charge. It stayed the same on both sides. It's still -1 on that side. Right? So we know that nothing in this one changed. All the oxidation reduction processes occurred with copper and silver. So copper went from a 0 to what? Well, if that's 2 times minus, that's a -2. This has to be a +2 because it's an ionic compound. Okay? So if we went from a 0 to +2, that means it was a loss of 2 electrons for each copper. Okay? And silver went from what? -1 here, +1 there. So it gained 1 electron per silver times 2 equals 2 electrons, right? 2 silvers, and only 1 copper, 2 electrons. So the electrons balance. And we're looking for the one that was oxidized right there. So copper is the reducing agent. Okay. Stop me if you have questions. Let's see. All right. We don't need to keep this up here. We're going to take a look at 3 reactions and try to classify them. Which reactions are oxidation reduction, and identify the oxidizing agent, the reducing agents. Okay. So let's do A, the first one. Zinc, yep. Zinc solid plus hydrochloric acid. We did this one in that lab. So what did we get? We got bubbles, right? We got hydrogen gas. Let's see, this is in aqueous solution and hydrogen gas. Yes. Let's see, balance, 2, 2. This should be 2, shouldn't it? Yeah. Okay, we're balanced now. All right, so is this oxidation reduction? Yeah, we don't even have to identify it as oxidation reduction. There's an element. It's in a compound here. So we know its oxidation state changed. It went from 0, and we have to assign a -1 here. And we can do that because this is an ionic compound in solution. Right? So all halogens, when they do the ionic number, they're always -1. So that means this has to be a +2. That's a 0. And it's a +1 here with a -1 there. Okay. So we went from 0 to +2, which means we had a loss of 2 electrons per zinc. And chlorine didn't change, but hydrogen did change. It went from a +1 to a 0. So there was a gain, 1 electron per hydrogen. Oops, not yet. Times 2 equals 2 electrons. Times 1 equals. Okay, so we need the oxidizing agent and the reducing agent. The oxidizing agent is reduced. So this is the reduced. This makes this one the oxidizing agent. Makes this one the reducing agent. Probably writing too small for the video. I'll write bigger. Okay, that is an oxidation reduction reaction. Zinc is the reducing agent, yes. Hydrogen chloride is the oxidation agent. Well, hydrochloric acid, it's in aqueous solution. Okay, how about the next one? So we're only given the dichromate ion, which means what? There's probably a counter cation in there somewhere. And it really doesn't matter. It could be sodium, it could be potassium, whatever, it's soluble. And they're saying that it's actually a spectator. So the cation doesn't change from one side to the other. So we're only interested in that one and that one yields CrO4 2 minus plus H2O. Okay. Let's see, this is aqueous. This is aqueous. This is aqueous. All right. We did this one before, right? This was a +6, correct? I think so. +6. Oxygen doesn't change from one side to the other. It's a -2. This is a +1, which gives us a -1 overall. This is a -2. This is a +1. They didn't change. How about this one? 4 times a -2 is a -8, but we have to hold 2 of them out. Right? That's a +6. No change. This is not an oxidation reduction reaction. And the last one. 2 copper 1 chloride, aqueous, yep, produces both a copper 2 chloride, aqueous, plus copper metal. Okay? This is a decomposition reaction. It's a special kind. I'll give you the name in a minute. But we know this is oxidation reduction because there's a metal right there. But there's an element out of that compound. So if this one's 0 and chlorine is -1, that means this has to be a +2. This is a -1. This is a +1. So notice that there are 2 of them here. One of those coppers went this direction. It lost an electron. But it only happened to one copper. So that's 1 electron. The other copper went here. And it gained 1 electron per copper. Times 1 equals 1 electron. Okay? So that makes this compound both the oxidizing agent and the reducing agent. Actually, one of those, there are 2 of them. One of them became the oxidizing agent and the other one became the reducing agent. And there's a special name for that. It's called a disproportionation reaction. Oh, I thought I had that animated. Let me write that up here. Reactions. Some companies use this reaction to generate copper metal. It depends on the source of their ore. Ores usually come out of the ground as solids. So in the process of extracting copper from the ore, one of the products might be copper 1 chloride as a byproduct. So they take that and go through a different stream and produce a little more copper out of it. All right. So now we're going to go jump from the practical to the theoretical. Try to understand some of this stuff based upon prevailing theory. This is the collision theory of chemical reactions. And that name is not particularly inventive, right? It just means that the reaction occurs because of a collision, right? In order for a reaction to occur, reactants must collide with one another. You have molecular collisions. That's the first proposition. You must have a collision. There's no collision, there's no reaction. There can be a collision and no reaction. In that case, the activation energy was not reached. You need to have enough energy in the collision to break the original bonds and allow new ones to be reformed. So there's a minimum amount of energy called the activation energy. And the other is orientation. When species collide, if they have enough activation energy, they have to be oriented correctly, because as the bonds break, new ones form. And if the bonds that you want to form would be from this side of this molecule and that side of the other molecule, not going to happen. So orientation is essential. All right. All right, this is just, I've already talked about that. Have to have collision. Need a minimum amount of energy. That's kinetic energy. In other words, they've got to be traveling, got to be moving with a certain amount of energy. And then they have to be oriented correctly. So this just illustrates, this came out of your textbook. This illustrates proper orientation and minimum activation energy in the collision. At the top one gives you products. The first one in the improper orientation has both oxygens toward each other, nothing happens. Nitrogen and oxygen toward each other, nothing happens. Nitrogen and carbon toward each other, nothing happens. You need the oxygen from the nitrogen dioxide to be part of the contact point with carbon from the carbon monoxide in order for the reaction to occur. Now, if we're trying to produce a certain reaction and we know we've got enough energy because it's hot enough, then how do we increase the probability of having proper orientation? You increase the concentration of your reactants, and that gives you more frequent collisions. And just statistically speaking, the more frequent the collisions, the more likely you are to have proper orientation. So increasing the concentration does that. If they're in solution, you increase their solution concentration. If they're gases, you increase their partial pressures. The number of molecules in the reaction mixture will be more likely to produce the proper orientation. Okay, 3 factors necessary. You got to have a collision. You have to have, well, let's see. What are the 3 factors? Okay. We're saying molecular collisions are required, yes. Low activation energy, well, that would be preferred, right? If you have a low activation energy, then you don't have to heat it up so hot. But you could have high activation energy and still get a reaction, but you'd have to add more energy to the reaction mixture and proper orientation. All right. We talked about exothermic versus endothermic reactions. Sort of touched on them, right? I'm going to leave that there. So when we define an exothermic reaction, thermic means heat, exo means out of. So when the reaction occurs, you can measure a temperature increase, or you can feel the heat coming off the reaction. Those hot packs that you can get in the hospital, It's got a capsule inside of the water bag and you break it. And as it goes into solution, it gets hot. That's an exothermic reaction. They have cold packs too. Break that capsule, mix it up, and it gets cold. It gets really cold, actually. That would be an endothermic reaction. Everything, when we describe endo and exothermic, everything is, the terminology refers to the system. What is the system versus the surroundings? So if we say our system is a chemical reaction, say we have sodium hydroxide in solution plus sulfuric acid as our reactants. They produce products. I'm not going to bore you with the products, but an acid base together is always exothermic. So the system, if this is the system and everything else is surroundings, right? This is the system. Then the surroundings feel an increase in heat. Okay, it signifies a movement of energy from the system to the surroundings. Vice versa. Right? If we had a reaction that was endothermic, then the heat would be moving in. And delta H is the term that we use for heat moving one way or the other. Let's see, burn propane, right? We know that's exothermic. We heat our house, cook our meals, barbecue, whatever the case may be. Now, in terms of the reaction itself, if we look at a graph where this is the progress of the reaction, it's moving from reactants to products, and this is the energy of all the reactants or all the products. So if we look at it in those terms, then if we have, this is the energy level of the reactants. And then we need to put in enough energy to reach this peak. That's the activation energy. So if we do this from here to here is activation energy. And we get products down here. Okay? The difference between this energy level and that energy level here is a difference in energy, or under certain circumstances, we can identify it as heat. Okay, so that means that the reactants had more energy in them, in the bonds here, than we had in the product bonds. That's exothermic. And remember, when you calculate a delta, it's final minus initial. So we take this value, which is lower, minus this value, which is higher, give us a negative value, right? So the exothermic means that this value is going to be negative. And that fits with our definition that everything is referenced to the system. If energy is leaving the system, leaving means negative. If it's added to the system, it means positive. And in order to draw the positive analog to that, actually we just run the reaction in reverse, right? Make these the reactants. We have to put this much energy in for the activation energy to go in reverse, right? So the reverse is more activation energy to get to here. And that's what you do with glycerol, nitric acid, and sulfuric acid. You make nitroglycerin. You store a lot of energy in the nitroglycerin molecule. Going this way, right? And all you need is just a little shock and boom. It's very unstable. In fact, Alfred Nobel's brother was killed by an accidental explosion. He and 4 other members of his team. So that pushed Alfred Nobel further to find out a way to stabilize the stuff. And eventually he did produce dynamite. He took the German word is Kieselguhr, which is diatomaceous earth. Right? It's the ground up product of diatoms, ancient diatoms that are stored in layers in the soil under the ground. And well, I'm not going to bore you with the details. That's enough for now. It's an endothermic reaction going this way, and then when it blows up, it's an exothermic reaction. Photosynthesis is an example of endothermic process. Only photosynthesis is a multi-step process. If we're talking about chloroplasts in green plants, we get electron movement in there. These are oxidation reduction reactions. We're taking energy from the sun and storing it in the bonds of molecules. Eventually, whatever storage molecule the plant prefers, super sweet corn stores it as glucose or sucrose, right? Field corn that you're going to harvest, let it dry and harvest and feed it to the cows, stores it as starch. That's why field corn it's not sweet. And that's also why if you grow super sweet varieties, actually they're cultivars, of corn in your garden, and everybody loves sweet corn, when you harvest that stuff, you want to pull it off the plant, shuck it, and throw it on ice immediately to stop that reaction, because there are enzymes in there that will continue to take that sugar and convert it into starch. So if you just pull the ear off and lay it on the ground, by the time you get home, it's no better than field corn. But photosynthesis is an endothermic process. We're putting energy into the system. And that's what it would look like. Just go the other direction. Start off with low energy, end up with higher energy. And the activation energy on that reverse reaction is much, much higher than it is the other direction. Which is another way of saying that this is the preferred direction for the reaction, to go that way, because at whatever temperature you're at, it takes less energy to go that direction. So it prefers to be over here. When we're making nitroglycerin, we have to heat it up to make it go that direction. All right. My goodness, we're losing people, aren't we? Where did we? The only one that told me he had to go was Mr. Bragg. Mr. Bragg. Yeah, Matthew. The rest of them just evaporated. What's the proper term for that? Disapparate, right? From Harry Potter. We need to put one of those barriers in here. You can't disapparate from this classroom. Which of the following statements are correct? Okay. During an exothermic reaction, the average energy of the products is higher than the average energy of the reactant. No, it's the other way around. During an endothermic reaction, the average energy of the products is lower than, right? They're just backwards. A and B are backwards from one another. C, during an exothermic reaction, the average energy of the products is lower than the average energy of the reactants. That's it. C is correct. All right. Okay, so now let's talk about reaction rates. In chemistry, if we look at this particular chart, and we're only interested in the energy level of the reactants and the energy level of the products, these two together define a discussion of equilibrium. That's a starting point for equilibrium. We don't care what happens in between. This part of the graph right in here, this talks about kinetics, which in chemical terms is reaction rates. How fast does the reaction go? Now, we're not going to go into as much detail as I do in my general chemistry class, but that's where it comes from, that discussion. So we're going to look at it more in a practical sense. What affects the reaction rate? What makes it go faster or slower? The physical nature of the reactants. In other words, if they're all solids, or a solid and a gas, or whatever mixture, the particle size makes a difference. Reactions occur at the surface of solid particles. That's why solutions are preferred when we can get them, because everybody is intimately involved with one another, or gases, right? Everybody's, they're uniformly distributed. If you try to react a solid with another solid, and you have a chunk of reactant here and a chunk of reactant there, and you just put them, the only place that a reaction is going to occur is where they touch. So the smaller particle size makes more surface area available, and the reaction will occur faster. That's why in mine inspectors are going to check your filters, and they're going to do air samples. They're going to have this device, and they're going to set it over here, and it's going to suck air through and filter out solid particles over a period of time. They have standards. And then they take it to the lab, and they look at the number of particles, the density of particles on that, and equate that to the amount of air that was drawn through it, and say, okay, you've got too much coal dust in this atmosphere for safety. So once it reaches a certain level, then all it needs is an ignition source, and you've got an explosion. So the small particle size of that coal dust makes explosions possible, very fast reaction rates. You can do that in grain silos too. If you have grain dust, if you have lots of grain in your silo and the dust builds up, and all you need is an ignition source, and that whole silo could blow up because of the particle size. Concentrations. If we have all gases, then increase the partial pressure of your reactants, and you're going to have a faster reaction because the probability of encounters increases. Or if you have them in solution, increase the solution concentrations, you'll speed up the reaction. Everything else being equal, right? Like equal temperatures, so forth. Reaction temperature will also increase the reaction rate because the temperature is a measure of average kinetic energy of all the particles in the mixture. So if you increase the temperature, you're giving them more kinetic energy, more of them will exceed the activation energy, and you have a faster reaction. And then the last one is the presence of catalysts. If you have a catalyst involved, what the catalyst does is it reduces the activation energy required for the reaction. Now, the reactants and the products are exactly the same with a catalyst, but the rate is faster. And the reason it's faster is because it doesn't go through the same mechanism, steps for this way as it does for that. The catalyst gives the reactants an alternate pathway to get to products. And that alternate pathway requires a lower energy. So that means more of them can react quicker. That speeds up the rate. It doesn't change the outcome at all. It just happens faster. So I've done an extensive discussion of this already. When we talk about the physical nature, we mean the states or the particle size. So the reaction rate will be faster generally between liquid state reactants than solid states, as a general rule. And gaseous state are even faster. Because in order to get our reactants in the gaseous state, you got to add energy to begin with, right? So you're edging closer to that activation energy, but just by producing gases. All right. So if we have smaller particle size for solids, we get a faster rate because it's all surface chemistry. Concentrations, right? More concentration means a higher probability of collisions. Increase the temperature, you make more of the molecules. Remember, temperature is a measure of average kinetic energy. So if you say like this, if you have temperature here and you have, let's see, percent of your total, then they're going to be something like this. At that temperature, you're going to have at least this much over here exceeds that temperature. So if you increase the temperature of your reaction, let's say, the temperature stays put and this shifts and puts more of your reactants in this zone over here with enough energy to meet the activation energy requirements. And then the catalyst. You have two types of catalysts: inorganic catalysts and organic catalysts. Organic catalysts are called enzymes. Now, they have some things in common, and enzymes have very specialized application, whereas inorganic catalysts could be useful for a multitude of reactions, whereas enzymes are specifically tailored for a particular reaction, or at most, a small handful of reactions. So, for instance, I think I've mentioned this reaction before, the Haber-Bosch process, where Fritz Haber was trying to take nitrogen from the air and fix it as ammonia. So he would combine nitrogen gas and hydrogen gas, and he wanted to produce ammonia. Well, this is an exothermic process, which means it preferred let me see, how do I put this? Let me balance it first. Let's see, 2, 3. As he increased, since it's an exothermic process, he wanted to have enough energy in there for the reaction to occur. The problem is it's exothermic. And when you increase the temperature of an exothermic reaction, you start favoring the reverse reaction to produce these, right? When you increase the temperature, now you make this direction more favorable, more and more favorable as you increase the temperature. So in order to overcome that, he wanted the reaction. We're talking about equilibrium. And what Haber decided to do was to use a catalyst, very finely divided iron. That would increase the rate in that direction. So even at those high temperatures, he still got some ammonia. And then what he did was he cooled the mixture down. He just drew off part of the mixture and cooled it. And the ammonia condensed at a higher temperature than nitrogen or hydrogen. So the ammonia came out of the mixture and the gases stayed there. And then he just took those gases and ran them back through the reactor. And eventually he got the, after 4 or 5 cycles, he got the ammonia up to 15 or 16%, which is industrially okay. Anyway, but he used finely divided iron as a catalyst. Now, that's an inorganic catalyst. An organic catalyst, which is used by rhizobia, which is a bacterium that resides in the roots of some plants, legumes. If you want to see some, find a healthy field of clover and yank a bunch up and look at the roots. Right? They'll have nodules on them if they're fixing nitrogen. They have nodules on them. Then take your knife and cut the nodule. If it's pink, then it's active. There's a compound in there that's analogous to our hemoglobin that moves oxygen into and out of. There's also an enzyme system in there that makes this reaction possible. It's not exactly that reaction, but it produces fixed nitrogen, ammonia. And then the plant and the bacteria take it further. Right? So you can make nucleic acids out of, DNA, RNA, or you can make proteins out of it. But those enzymes, the similarity stops with speed of reaction. They both speed up the reaction, but enzymes are very specific. And most often, not all of them, but most of them go only one direction. So if you want a reaction to go one direction under certain circumstances, and you want it to go in reverse under other circumstances, it takes 2 enzymes. One goes one way, one goes the other way. That's how your body controls reactions so that you don't get cells that are just doing whatever they want. And enzymes are very sensitive to temperature and other environmental conditions, but temperature in particular. So the enzymes in our bodies function at their highest efficiency at around 98.6 Fahrenheit or 37 Celsius body temperature. For dogs and cats, their enzyme systems function best at about 102 to 103 degrees Fahrenheit. Okay. So when your body temperature gets up to 103, 4, 5, your enzymes are being cooked. They're not working at those high temperatures. I mean, there are other physiological effects, but that's one of them. All right. This demonstrates the decrease in activation energy required for a catalyzed reaction. All right, what's the function of a catalyst? To increase the reaction rate by decreasing the activation energy. Now, I mentioned equilibrium. Equilibrium, actually the definition of equilibrium in chemistry is if we have a reaction, let's be more general. Let's say we have an X plus a Y and it yields an A plus a B, just in general. We have a reaction rate going this direction, right? One a rate going that direction, but once you build up a certain amount of product, you get a return reaction going this way. Now, they don't have to be, initially, they're not the same rates. If you put all of X, Y in there and no AB, then for a while, it's always that direction. But eventually, you get enough of this built up that you get a return reaction, and once those reaction rates balance, you have equilibrium. So for that reason, when I do my general chemistry class, actually second semester, we study kinetics first and get reaction rates working in our brains. And then we move to equilibrium. All right, this is another way of looking at it. For two hydrogen iodides yields hydrogen plus iodine element. Then the reaction rate forward starts to increase to a point, and the reverse reaction, actually, the top is the forward reaction. Hydrogen plus iodine yields a hydrogen iodide. Okay, it decreases over time as the reverse reaction increases, and we reach a point where both reaction rates are balanced. All right. This is another way of looking at it. The first one was reaction rates. This is in terms of concentrations. So if you look at, actually, let's clear the board so I can talk about it in terms of concentration. I'll leave that there. So if we're looking at concentration, and we have time here, concentration here, then the product concentration, if we're looking at this reaction where we have iodine plus hydrogen yields 2 hydrogen iodides, then at the very beginning, we start off with a certain amount of iodine and hydrogen here, reactants. And as time progresses, they decrease because they're making product. But the amount of product that's being produced is twice as much as either one of those. So it goes up twice as fast. So if we eventually reach a point where this product is balanced with these two reactants over time. And that's usually the way we measure. We measure concentration, and then we do some calculations to find out what the rate is. What we're assuming with this scenario is that the reaction is reversible. In other words, it will go in both directions. And what we usually do is we use half barb arrows. That's forward direction, that's reverse reaction. Now, for practical purposes, if the reverse rate is very, very, very slow, then for all practical purposes, we can identify the reaction as irreversible. In other words, it produces this, and it takes a very, very long time to detect any of the reverse reactions. Okay. A state of blank is reached when the concentrations of all reactants and all products remain constant chemical equilibrium. Is the first blank. And a blank is one in which the conversion of reactants to products and the conversion of products to reactants occur simultaneously. A state of concentrations of all reactants. Chemical equilibrium first. Reversible is one in which the conversion occurs simultaneously, forward and reverse. All right. Okay, so we're given, so if we look at equilibrium in terms of individual concentrations of reactants and products. For this particular one, where we have water reacts with carbon dioxide, and this is in a closed vessel, obviously, because they're all gases, then the forward reaction produces hydrogen gas and CO2. But if we're saying that the forward rate and the reverse rate are balanced, and now we're at equilibrium, then once you reach equilibrium, then macroscopically, what you observe externally is that concentrations are equal and they don't change. Right? But we know underneath, microscopically, the forward and the reverse reactions are happening at furious rates. It's just, we don't see the difference, right? Because the rates are balanced. So when we measure concentrations, we could care less. Unless you're trying to understand what the process is. But if it's at equilibrium, then what would happen now if you add more water, water vapor to that reaction vessel? Think of it in terms of the collision theory. If you add more water molecules to the reaction vessel and it's at equilibrium, then you're going to have more possible collisions with the carbon monoxide that remains, right? So the reaction rate is going to increase in the forward direction for a little while until you build up enough product to get the reverse reaction to balance it again. So for a time, you're going to shift the reaction toward the right by increasing the water vapor. If you add more hydrogen then, a similar thing happens only in the reverse reaction. And you increase the rate in the reverse reaction until you build up enough reactants again to get the forward reaction now rates to balance the reverse reaction. Okay. And I just introduced you to Le Chatelier's principle, which we'll talk about in more detail in just a minute. The equilibrium, once we've established equilibrium and the forward and the reverse rates are equal, and we measure concentrations of reactants and products, we can express that equilibrium by a single value. Now, I need to change that slide. I'd rather write it this way. That way the coefficient is more easily identified with the reactants and products. So this is the coefficient for A, this is the coefficient for B, and they produce C and D with those coefficients. Okay? When we write the equilibrium constant, and it's only constant for a given temperature. If you change the temperature, the equilibrium constant will change. Okay. So for a constant temperature, the equilibrium constant then is products concentrations to the coefficient powers divided by their reactant concentrations to their respective powers. That's the equilibrium constant. And this is also known as the law of mass action. Okay. When you see this in terms of square brackets, square bracket around something like, well, let's say we had, what was that previous one? Let's put actual number values in here. Water, carbon monoxide. Let's do that one. Right. Water is a gas, carbon monoxide, and it produces hydrogen gas, right? Plus CO2. Yeah. The coefficients here are 1, 1, 1, and 1, right? So if we wrote the K for this one, we would have hydrogen concentration, carbon dioxide concentration, both to the first power, divided by water vapor concentration times carbon monoxide concentration. When you see square brackets, those represent molar concentrations, molarity, moles per liter. Right? So for a liter, say we have a 1 liter container, then if we had 1 mole of hydrogen at equilibrium, it would just be 1 molar would go in that value. We put those values in, multiply them out, and you get your equilibrium constant. We can also express those in terms of partial pressures, right? Dalton's law of partial pressures. If we do that, then this Kp would be the partial pressure of hydrogen times partial pressure of CO2 divided by the partial pressure of water times the partial pressure of CO. And those two values, these are usually in atmospheres. But the units of measure determine what K will be. So we can do it either way, but the value will be different. They're related, but we're probably not going to get into that. Okay, another caveat. If we have a reaction in which a reactant or a product is either a solid or a pure liquid, those values do not enter into the calculation because solid concentrations don't change and pure liquid concentrations don't change. So we're only interested in, for our purposes, aqueous solutions, say their molarity, and gases. And everything else we leave out of the expression. All right. Temperature, I mentioned temperature. If temperature changes, what effect does it have on the equilibrium constant? If we have, say, this reaction and it's exothermic, we treat the heat term as a product because it's being given up. Well, if we increase the temperature on this, what's going to happen? You increase the temperature, you've increased that term, and that drives the reaction back this way toward equilibrium. So that increases the denominator, which decreases the K. Right? If you increase the denominator, you decrease the quotient. Okay. But if we put that delta H on this side, say it's endothermic. Now, if we increase the temperature, then it drives the reaction this direction. And this increase in temperature will increase the products, which will increase the numerator. And that will increase the K. All right. Another way to look at these Ks. So let's forget temperature for now. For in a reaction, if a K is very large, that means that products are favored. If the K is very small, reactants are favored. So when they reach equilibrium and you measure the amounts, you're still going to find with a small K, you're going to find a lot of product is still in there. If the K is very large, then you're going to find a lot of, did I say product? A lot of reactant is still in there. If it's very large, you're going to find a lot of product and very little reactant left. Now that's a discussion of the equilibrium constant of the effective temperature and the size of the equilibrium constant. Now, the equilibrium constant is constant for a constant temperature. But if we start off, say, with different concentrations of reactants, and one test goes this way, one experiment goes that way with high concentrations, and we run it again with low concentrations, we're going to end up with different concentrations in each experiment. They'll be in equilibrium, and this will be the same as long as the temperature is the same. But the equilibrium position will be different. The equilibrium position takes into account the actual concentrations. All right. This just summarizes everything. It's straight out of your textbook. So what's the equilibrium constant expression for this reaction? If you assume no solids and no pure liquids, then all the terms enter into the value. Right? So we'll have HI in square brackets to the second power divided by hydrogen times iodine, like that. Now, we've been discussing Le Chatelier's principle quite a bit. We just haven't named it. Le Chatelier was a Frenchman, obviously. And he noticed this effect on equilibrium when you change reaction conditions. At this point, the only two reaction conditions we've changed are concentrations and temperature. Right? There's one other one that I'll throw in a minute. But we have a feeling for what happens. And Le Chatelier simply said that when a system is at equilibrium, any stress that's applied to the system will be met with a response from the system in some way to reduce the effect of the stress. Right? So if it's at equilibrium and we stress it by adding A, it's going to use up some of that A until the stress is relieved and we get a balance again. Or even if we remove some B from an equilibrium system, then the reaction is going to move back this way to replace part of it. Okay? And if you have an equation that expresses a reaction and you say it's at equilibrium, and the question is, which way will it move if we do something to it? Say we add A. If you say it moves to the right, that only has meaning if you're referencing a balanced equation. If you don't have the balanced equation right there with your statement moves to the right or moves to the left, then right and left don't mean anything. Because all I would have to do is just flip the equation around and your right becomes my left. Okay, we talked about concentration changes as a stress. And we know that if we increase the concentration on this side, it moves that way. Increase on that side, moves this way. Decrease on that side, it moves that way. Decrease on this side, it moves that way. That's the easiest one to visualize. Now, the equilibrium is reestablished, and the K is going to stay the same as long as we don't change the temperature. But the position might change. In other words, if we remove some B, then we're going to decrease the concentration of B. Now, the system is going to respond to produce some B, but not all that we removed, just till you reach equilibrium again. So now we have a new position, an equilibrium position. All right. And this is one way of showing the difference with the Haber-Bosch process. I'm not going to beat that horse anymore. Temperature, we know. Temperature will affect the K, and that will affect the equilibrium. But for practical purposes, right, just for understanding which way the thing's going to move, if you know that the reaction is exothermic, then you put the heat term as a product, and then you can say, what effect does temperature have on it? And also for endothermic, you put it on this side, and then you can discuss the equilibrium in terms of Le Chatelier's principle without having to deal with understanding this. Right? That's actually what's happening. Right? But when you put the heat as a term on one side or the other, then you can see a change in that term as a stressor. This is just an example of an equation, a reaction in which the cobalt tetrachloride ion produces the blue color, and the pink color is the hydrated cobalt. So if we cool it down, that means we've reduced, see the delta H on the right-hand side? Right there. It's exothermic. So if we cool it down, we're removing heat. And that removes the delta H from one side and forces the reaction to the right. That's why when you cool it down, it turns pink. Okay. This is the one that we didn't discuss yet. And that's the effect of pressure. Pressure only has an effect in terms of Le Chatelier if there are gas terms in your reaction. And we're using the Haber-Bosch as an example. These are all gases. So all three terms are in the equilibrium expression. And it's exothermic. Right? In case we change the temperature, then we can do that. But if all we're doing is changing the pressure, how do you change the pressure? Well, one way is to add more reactant or product, right? And that would invoke I'll think of it in just a second. Or not. We've already studied what happens when you increase the concentrations, right? But what if you increase the pressure without changing the ratio of the various reactants products? In order to do that, you change the volume. Right? If you want to increase the pressure on the whole system, you decrease the volume, right? That's Boyle's law. Avogadro talked to discuss the addition or subtraction of various components like that. So we've already talked about that one. Pressure then, if we have this system, say it's got a movable piston, and you got the reactants in here, and you squeeze it, right? Just move the piston down, decrease the volume, increase the pressure. How is the system going to react? The system only changes its equilibrium position if the moles of gas on one side are different from the moles of gas on the other side. In this side, we have 2 moles total of gas. On this side, we have 4 moles total. So if we stress the system by increasing the pressure, it's going to decrease that pressure somewhat by producing fewer moles of gas. Right? That's what happens. When you decrease the number of moles of gas particles, then you decrease the pressure. And that's its Le Chatelier response. So if you have 4 here, 2 there, and it's at equilibrium, then if we increase the pressure, it's going that direction. Okay. If, on the other hand, we're down here and we go up like that, now it's going to respond by producing more gas, and they'll go this direction. Oh, that's the other thing that Haber did when he was developing the procedure. He didn't just increase the temperature, he increased the pressure enormously, like 200 bar, 200 times the atmospheric pressure. So increasing the pressure helped drive it that way also. All right. So another way you can increase pressure is to inject an inert gas or any gas that's not part of the reaction and will not react with any of the reactants or products. If you do that, nothing happens because you're not changing the relationship of one side to the other by adding an inert gas, for instance. All right, so just changing the pressure doesn't automatically move the equilibrium. If you have the same number of moles on both sides, you can change the volume all day long and it won't matter. How about equilibrium in a catalyst? Catalyst has no impact on equilibrium. All it does is you get to the equilibrium quicker. If you're not at equilibrium at start and you put a catalyst, then you get to the equilibrium a lot faster. But if it's already at equilibrium and you add a catalyst, doesn't matter. The movement forwards and backwards will be by an alternate pathway, but it won't change the reactant product ratios. Okay. You can affect, Le Chatelier principle refers to concentrations changes, temperature changes, and pressure changes under the correct circumstances. All right. 12:30. Okay. We got a half hour. We can take a look at these. Anybody ever had to breathe into a breathalyzer? You know, like a traffic stop somewhere. Usually at those traffic stops, they just shine a light in your eyes and see what your pupils do most of the time. And they might check your license. They tend to do that during holidays when people are more likely to drink and drive. They'll set up sobriety stops. But if you breathe into a breathalyzer, this is one chemical reaction that's used, and it's an oxidation reduction reaction. Potassium dichromate will react with the ethanol in your breath, and that's correlated to the amount in your blood serum, plus some sulfuric acid in the mixture. And it will produce a chromium sulfate. Now the dichromate has a +6. Let's see, what does this one have? 2 chromiums and a sulfate. All right. And there are 3 of these. Okay. So this sulfate, yeah, sulfate didn't change. So that's a -2. That's -6 total. And this has to be a +6, +3. So the chromate went from a +6 to a +3. It was reduced by the ethanol. And then the ethanol was oxidized from the ethanol on the left to acetic acid on the right. And I'm not sure which one they measure. Probably the easiest one to measure is the presence of acetic acid, because you can measure pH. And we haven't talked about that yet. But you can measure the acidity in the solution. And if it increases, no, you can't do that because of sulfuric acid. All right. How do we do that then? It could be spectrophotometrically, shine a light through it. The absorbance of chromium-6, well, I didn't put it up here. The light absorbance at a given wavelength for chromium-6 is different than chromium-3. That's probably the way they do it. They just measure the change in absorbance between the two. And that's correlated to the amount of alcohol in your breath, which is also correlated to your blood serum alcohol. All right, so after saying all that, in this reaction, blank is undergoing reduction. That's the chromium, right? Chromium-6 is undergoing reduction to chromium-3+, while blank is undergoing oxidation. Well, in that case, ethanol is undergoing oxidation to acetic acid. So let's see. Oh, I got it animated. All right, there's 6+. And that carbon, the carbon that's attached to the hydroxyl in the ethanol versus the carbon that's attached to in the carboxylic acid group on the right. The other carbon didn't change, but that carbon did. It went from a -1 to a +3. So chromium-6+ went to chromium-3+, while ethanol went to acetic acid. That means the dichromate is the oxidizing agent, causes the reduction of the other one, and is the reducing agent. Okay. Oh, there was only one. Okay. Sometimes they have two. Any questions? That's enough for one day, huh? An exam and a whole new chapter. That's the nature of the beast. We'll be back next Friday and do chapter 10 on acids and bases and salts. And then we'll follow that with a lab, the osmosis and dialysis.